We want to find the voltage V of t across this 7 ohm resistor in this circuit as t goes to infinity. As usual, we want to develop a plan for what we want to do, so let's take a look at what's important about this. The input's a sinusoid, and we want to find the particular solution as t goes to infinity, so this V of t is going to be the same form as the input, so all the signals are going to be sinusoidal in this system. So we want to do frequency domain analysis, which means that we're going to want to use phasors for our voltages and currents, and impedances for our circuit elements. Now, as far as an overall approach, generally the first thing I'll try is circuit reduction, and it looks like what we can do is find an equivalent impedance for this entire set of components here. These two are in series, those are in parallel with this one. That whole set will be in series with this impedance. So we can come up with a voltage divider. So it looks like we have some input voltage as a phasor, a 7 ohm resistance, and then some equivalent impedance, call it ZEQ, and we want to find the voltage phasor here. So the voltage phasor V is going to be Vn times 7 ohms over 7 ohms plus ZEQ. So if we find the equivalent impedance of this whole mess over here, we're home free. So let's convert this circuit into the frequency domain per our analysis here, and then use this voltage divider formula. Determining the individual impedances of the circuit elements, this 7 ohm resistor has an impedance of 7 ohms, this 4 ohm resistor has an impedance of 4 ohms, those are easy. The impedance of this inductor is going to be 3 henries times 2 radians per second times J, so this is going to be J6 ohms. This guy is going to be J times 2 radians per second times 1 henry, so this is J2 ohms. And this impedance is minus J over 2 radians per second times 1 over 4, which is minus J2 ohms. So let's redraw this circuit with all of our stuff in the frequency domain and then do our analysis. Okay, as I mentioned earlier, these two are in series, so I just add their impedances. So this is 4 minus J2 ohms. Then those in parallel with this guy here is going to be the product of the two, so J2 ohms times 4 minus J2 ohms over J2 plus 4 minus J2. This becomes pretty easy in rectangular coordinates because the denominator is a real number, so this becomes J8 plus 4 over 4. So J8 over 4 is J2, 4 over 4 is 1, so that impedance is J2 plus 1 ohm. Now I add that in series with this J6, and ZEQ is equal to J2 plus 1 plus J6 ohms, which is J8 plus 1 ohms. Using my voltage divider that I talked about already, V as a phasor is going to be the input phasor voltage, 3 at an angle of minus 30 degrees, times this impedance, 7 ohms, over this impedance plus the equivalent impedance of this whole set of stuff over here. So 7 ohms plus J8 plus 1 ohms. That becomes 3 at an angle of minus 30 degrees times 7 over J8 plus 8, which is 21 at an angle of minus 30 degrees, multiplying this by 7, divided by the magnitude of this is going to be 8 square root of 2 at an angle of 45 degrees. So V as a phasor becomes 21 over 8 times the square root of 2 at an angle of minus 30 minus 45 degrees is minus 75 degrees. So V of t is 21 over 8 square root of 2. Cosine of the frequency is still 2 radians per second times time minus 75 degrees. And there's our answer.